So, sure. Shall we begin?
Yeah.
Okay. So welcome everyone to the afternoon sessions. I'm Yan, the session chair of session 3, Deep Learning with Biomedical Data. So our first talk is an invited talk to be delivered by Dr. Jeffrey Fox. And the title is Deep Learning for Biomedical and Science Time Series. Dr. Jeffrey Charles Fox received a PhD in theoretical physics from Cambridge University while he was a senior wrangler. He is now a distinguished professor from engineering, computing, and physics at Indiana University, where he is the director of the Digital Science Center. He has supervised a PhD of 73 students and published around 1,500 papers in physics and computing with an H index of 82 and over 38,500 citations. He received the HPDC Achievement Award and the ACM IEEE CSCAN Kennedy Award for foundational contributions to parallel computing in 2019. He is a fellow of APS and ACM and works on the interdisciplinary interface between computing and applications. Without any further delay, let's welcome Dr. Fox to give the talk. Thank you.
Okay, can you hear me?
Yes.
All right, so thank you for the honor of this invitation. And I wanted, in this quick talk, discuss a little bit about deep learning for biomedical and science time series. And that's an abstract, okay. And we're going to apply it to some COVID data, but it's more broadly useful. And it's with my colleagues, Lesversky and Pine. And the motivation for this work comes from this strange picture here, which was actually chemistry, the Lennard-Jones potential. So that is a time series. If you look at the particles, here we have 16. And so there's some standard differential equations you can use to describe the time evolution of those particles, but you can also teach a deep learning network, a recurrent neural net, to predict the future of the Lennard-Jones potential. And the remarkable thing is, which is illustrated here, though you won't have time to study it, is that the recurrent neural net actually can predict 4,000 times further forward in time than the traditional standard ODEs, the standard applied math. And that's sort of pretty interesting. It shows that you can derive an operator which embodies a lot of interesting expertise. And that can obviously lead to significant speed up. Although each operator is a more complex operator, it predicts a lot further in time. And there's some demonstrations here that the error is essentially constant out to very large time, far past the time that you train the data. All right, so now we're going to try to look at other operators. And so if you think, as I say, if you think of differential equations or coupled ODEs or PDEs, then the new values of the velocity and position are equal to an operator on the previous values. And I say applied math tells you the correct difference equations or spectrum methods. However, deep learning gives you a different operator, but it's still an operator. I mean, in deep learning, you feed in the inputs and out pop the outputs, the predicted values. And so it is an operator. That little neural net, or actually probably quite a large neural net, is an operator. And I think it's pretty interesting to derive a set of operators to describe everything we can think of. And when I was a child, which was quite a long time ago, I was taught never to have high order approximations. Do have very simple difference operators. They're the most reliable. Whereas, of course, these neural nets are really complex, hundreds or even millions of parameters in some of these cases we'll look at. And they give better answers than the traditional methods. Whereas previously, and that's of course because of the activation layers and other things, stopped the explosion from the high order approximations. So here we're going to look at COVID among other cases. COVID is the one I have most results on. So we're just looking at some counts, which is a time series, is the daily count of infections and fatalities for 110 cities. But we also have some more other information of interest. Namely, for each city, we have some data describing the city, which for this particular applications are things like the percentage of people with high blood pressure or seniors or Hispanics or with asthma and so on. And that sounds relevant because if I think about that Lennard-Jones potential, when I have a differential operator, the parameters of the potential go into the operator. So when I describe some time series, I'm going to expect to put parameters into that operator. And these parameters could be thought of in this case as demographic properties. I will also come to a very well-known model from the University of Washington, but that's we'll look at that later. And we're going to effectively provide surrogates, deep learning surrogates for either the University of Washington model or the actual data. And I think at the moment we've done as well as we can with the data we have. Our data is not, was actually needs to be updated. I just got a whole new set of data. I haven't run it through yet, but we will very soon. I don't think it will affect the main conclusions. All right, so we were discussing the importance of industry. So if you look at time series, I believe the most important work in time series is done by the ride-hailing industry, that's Uber and Didi, plus some academics, and the natural language processing area. And if you look at the methods used, there are two methods here. The one in the middle here, which is a simple recurrent neural net with a couple of layers of LSTMs. And then on the right, we have a transformer network, which consists of a so-called attention gathering module called the encoder. And then when this is used in natural language processing, you have a similar decoder, but for the time series, I'm using LSTMs as the decoder. And in all cases, when you do time series, we need to look at attention. And we'll have some remarks on that very soon. Here is just an illustration of the pure LSTM model, and it's only till May 25th, and it's summed over this particular summary is the number of infections and the number of fatalities as a function of time until May 25th, and the blue is the prediction, the orange is the actual measured values. As is well known, this data has very striking weekly structure because people don't die on the weekends. That's a sort of interesting feature of fatalities and actually also cases. This is the input data is fitted separately for each city. This particular summary is summed over cities. And the variable used here is the square root of n, because we're using a root mean square error. And if you take square root of n, counting errors have constant, counting n plus or minus the square root of n is square root of n plus or minus 1. So that means it's the loss function represents the expected error. And you feed in a window which can go from 5 to 13. Here we show 13, and they all give good results, with the 13 for this case giving somewhat better results for the weekly structure. But here I try to generalize it to explain the general problem, because there are a large number of problems, both biomedical and science, of this type. And so you start off with a set of data, which are the blue dots, and in the horizontal axis is space. By space, I mean different data sources. For my COVID case, space is different cities. I have 110 locations along the bottom. They do not have to be next to each other. And then I have the time series, which was 115 in the case of data I had. And then the basic idea of this of all these models is you have a basic data unit, which is one spatial position and a time window, where that time window begins at any point in the time sequence. And then you're allowed to predict, you feed in input properties, and it's very important to know that these input properties are either the static properties or the dynamic. I explained why the analogy with Leonard-Jones potentials suggested we wanted to think of the static properties simultaneously with the dynamic, because they're closely linked. And then we have two types of predictions. You predict things at the same time. That's called sequence-to-sequence mapping, and that's actually what natural language processing is, but also is what in science, when you do things like measure the rainfall, predict the runoff, dependent on the details of the region you're in, or what we're doing here, forecasting the future. So we have a whole set of these things here, these windows. And just a minute, sorry. We should come back to this slide here. So these windows are either fed into this LSTM or they're fed into here. And then they get, when they're fed into here, they get so-called attention. And this attention is either some sort of little, essentially it's a little matrix operator operating on the data, and it compares the current time and space points to the time and space points at other spatial and other time positions. And so that's the key idea in the transformer networks. And with the recurrent networks, you're just looking at attention in time, not in space. So anyway, we did an analysis. I showed you the results of the pure LSTM. I just finished some results with the addition of the transformer network, which has only been looked at in a few places for science time series like this. And you have to do some funny things, which strike me as a bit odd, but seem to be work. Then you add to your data so-called positional or temporal encoding, such as series that vary with a weekly structure, because we have weekly structure in the data, and and the hybrid one, the one which has both transformer and recurrent, is about 20 to 30% lower in loss value than the pure recurrent. And here's some examples from the hybrid model. And it actually, so you can see it gives much better description of the weekly structure. And it's significantly lower loss value. And the loss normally smoothly goes down. Here's a catastrophic thing where the final loss isn't too bad, but it had you can see how these finding optimal values from deep learning doesn't always work. This had a catastrophic epoch where it went astray. Anyway, these results are clearly quite accurate. They even notice these deep learning networks are predicting what's recorded. They're not predicting truth, because I don't believe this weekly structure is, well, it's true, but it somehow doesn't represent the fundamental biology. It just represents reporting. Anyway, and here is the fit to this Washington model, which is essentially perfect, because that Washington model has no fluctuations in it. So there's a summary of this particular. I only have 2 minutes left. So with summary, I suggest that these time series models are very encouraging, and they effectively give you a surrogate for the differential operator, where you can determine the parameters of that surrogate operator from the data itself. And you can, in either biological opportunities here, epidemiology itself, or things like virtual tissue dynamics, which we work on at IU. The last couple of minutes, I want to just mention, we were discussing the importance of working with industry. So I have spent a lot of time over the last 18 months working with an organization called MLPerf, which is an industry consortium with around 80 organizations in it. It has a combined effort of about 50 full-time equivalents, and it is proposing and accepting the responses for a whole set of benchmarks. And these benchmarks cover areas you can see on the left, which correspond to different working groups. And here is the just release, well, it's not quite the, this is the version, this has actually just been superseded by version 0.7, and it is the, actually this is 0.7, not 0.6, it's mislabeled. And anyway, you have here the different benchmarks. You can see here my industry is very specialized. There's image benchmarks, translation, voice, recommender engine, and play and go. And then you have along here the submissions from which are dominated by Google, Alibaba, and NVIDIA. And you can study this as quite, you can look at the parallel efficiencies and things like that. And so we've set up a corresponding science data working group in MLPerf. And if anybody's interested, please contact me. We're trying to collect challenging scientific benchmarks to test and motivate new deep learning solutions. And so there are currently no directly scientific benchmarks in that set. And here is, well, let me finish that. So in my last 10 seconds, which I just overrode by a minute, I think I've tried to explain that spatial time series are pretty promising. There's a lot of new deep learning algorithms for them. They combine recurrent neural nets and transformers. And I think we were discussing applications. So I'm also looking at hydrology and earthquakes. And there actually is some work on hospital data using similar ideas, but not not that many studies of medical time series. And I suggest that this work can be done not only directly on the data, but also in terms of benchmarks in MLPerf. And that's it. Thank you.
Thank you.
Yeah.
So any questions?
Yes. Jeffrey, this is Jake. Yeah, it's great talk. I want to ask one more of fundamental questions. You showed the using deep learning to predict the curves up until the lockdown was over, and that was pretty good in predicting the subtle, finer details. And then I wonder why you think that deviating from your physics background and physics-based models and switching to deep learning is a better approach.
I think deep learning is incredibly promising.
Okay.
I believe that deep learning has not been fully, there are many more discoveries that can be made with deep learning. I may be wrong, but I am incredibly impressed by the capabilities that deep learning has shown.
So one hypothetical scenario is if you look at the data after the lockdown, and it's actually because of the influenced by the health policy and people's behavior, and all of the things will completely change. Would deep learning have predicted that, or a physics-based model would actually be better at?
Well, it all depends what data you put in. If you put in mobility data, then you would naturally predict it. If you don't put in, and you see, remember, these predictions are a little non-trivial. They are predicting from, say, a week's worth of data, or 9 days worth of data, or 35, 9, or 13 days of data, the next data. So they're using the immediate past to predict the future. But obviously, if the situation changes, that's like a physics problem. If the Leonard-Jones potential changes parameter in the future time, the model without that change in parameter won't give the right answer. But I say you can feed. We didn't actually use it because it was a bit rough, but there obviously is mobility data from about the use of cell phones, which is very clearly correlated with, well, say, cell phones in work, which is strongly correlated with the policies that reduce the infection rate.
Okay.
But these are all extensions. I would say that, as far as I know, these methods give better answers than all previous methods applied to this type of problem. And the reason is that remember what deep learning does, it's learning the hidden variables. So they're the hidden operators which are implied by the data, and it's learning them. So I think deep learning will succeed whether there is really where there is an operator, but we just don't know what it is because it's a complex social system or something which we can't properly model.
Thank you. So I have a question about maybe a little bit more details that maybe I missed it. So how long into the future, how many days into the future does the model predict? And
I predicted 14 days into the future.
Oh, okay. So that results actually 14 days into the future, and the curve matches. So
I mean, you can predict if you have. I mean, it's sort of trivial. You just use the data. You just train the data on for the time series which you have data 14 days into the future. You train it on that. So you just you could actually train it. Well, especially now with new data, you could train it a month into the future if you wanted to. I probably will look at that.
Yeah, the thing that I feel very impressive that because if you look at the curve that you shared in one slide, it's ups and downs for many modes, for example, but you actually capture all those modes. All right, so this is kind of impressive.
Well, it's not me, it's the deep learning network that's so clever. It just learns it learns the operator. So if you think there is a secret operator, the one problem which I think might not work is earthquakes. Because if earthquakes are totally random, there is no operator. And I'm worried that earthquakes are because they're phase transitions, which are very, very sensitive to totally random effects, the actual occurrence that it may not be effective. When we looked at earthquakes, when we apply it to an earthquakes predicted by a theory, we got perfect answer. When we apply it to the real earthquakes, we don't get a good answer at all at the moment. And I think it's really sort of a fundamental reason. These methods work when there is an operator or a theory, but we don't know what it is.
So another question is about so you showed on page 9 there are 2 dimensions. One is the city, the other is time. And for the city, do you actually use the correlation between nearby cities or actually each city?
No, I didn't. You could add that in, but these are just separate points and the correlations are coming from the data. Namely, what's being correlated through the attention mechanism is the correlations between the properties, like the fraction of people with asthma and things like that. And so this sort of standard dot product attention mechanism can capture such correlations. So my understanding is in these methods, you run multiple so-called heads, and so you look at a lot of different. You try to find lots of correlations.
I see. So my understanding for each city, you basically run the model to predict for that city, and then you do have like the features for each time step, like how many people are senior and how.
Sure, you can feed all of that in. You can. These methods are what's another surprising feature about deep learning is they're very robust. If you feed in too much data, it doesn't actually usually matter. It just ignores it. It finds the feature, at least if you train for long enough, it will find my experience has been it finds what's important.
I see. So basically, do you mean that you actually fit all the data of all the cities together as a one high dimensional tensor into there and get the prediction, which is also for all these cities out into the model, or?
Well, I mentioned when I did the transformer, where it's looking at attention, I actually, to reduce the computer time, which is, I did simplify it. I looked at attention and time only, and we fixed the space point, looked at attention and time, and then I fixed the time value and looked at attention in space. And so my attention size was number of time values plus number of cities, whereas the simplest model will be number of time values times number of cities. I will also look at that because it's trivial with the code to do either. But I started with the smaller problem. But this is all ad hoc. You're trying to put into the model what you think might affect the operator, and I just thought that intuitively that there's some features coming from the time dependence and some features coming from the space dependence, and the space dependence is not terribly time dependent. It should be largely fixed.
Yeah. So there's like a graph convolution that can model these states as a new operator. Yeah, so my last question would be, you mentioned the transformer as the encoder and the LSTM as a decoder. That's the best model you find. So is there any like insight on that? You mentioned that it could be from those ride sharing.
Well, the encoder one, the one that has the attention encoding, just has more information. Because it's feeding into the recurrent network. In that model, we feed in the actual input, which we would normally feed into the recurrent network, plus the information from the attention, the multi-headed attention operator. So essentially got two pieces of information, the actual data and the attention analysis, and it's just running that through the recurrent neural net.
I see. So my question would be like for the decoder side, why it's still an LSTM, for example?
Sorry, I missed that question.
So your decoder side to get the predictions is an LSTM network, right? So why this is better, for example? Yeah.
Well, there are people who've used a conventional transformer for the whole system.
Yeah.
I can try that. I started off by just converting the encoder from the NLP to science, and then I didn't convert the decoder. My guess is that this hybrid model is better because it's giving you two things. Because the recurrent neural nets have real value and they have real insight. So I'm trying to get the best of both worlds: the attention world and the recurrent neural network world.
Well, thank you. Any other questions from the audience?
But there's surprisingly little work in this area. There are only about two or three papers published using transformers to look at what I would call technical time series.
Okay, so if there's no questions, let's thank Dr. Fox for the impressive talk again, and we will move on to the next talk. So let me share my screen. Sorry. So can everyone see my screen?
Yes.
Oh, okay. Thank you. So the next talk will be delivered by Kyohei Kyoyama. Kyohei, are you here?
No. Oh, yes.
Yeah. Just want to make sure you're here. Okay. So I will first play the video, and then there will be a Q&A where you can answer the question. Right. So okay. Our next speaker is Kyohei Kyoyama, and the title of the talk is Cross-Attention DTI, Drug-Target Interaction Prediction with Cross-Attention Module in the Line Evaluation Setup. Let me stream the video.
Hello everyone, and welcome to our talk on cross-attention drug-target interaction prediction. Today we will focus on how we have optimized our model for industrial.
Okay, let's begin.
Hello everyone, and welcome to our talk on...
Okay, can you hear my computer sound?
Yes.
Yes.
Okay, let me reshare because I guess when I share, I actually clicked the sound. Okay. Yeah, let's begin.
Cross-attention drug-target interaction prediction. Today we will focus on how we have optimized our model for industrial applications. Interactions between proteins and non-protein compounds are ubiquitous events in living cells. They are an integral part of normal molecular biology, defining the nature of cells, tissues and whole organisms. Many drugs are non-protein compounds, and are developed for their interaction with proteins. The discovery of drugs which will activate, inhibit or otherwise affect functional proteins is the basis of many medical interventions. Drug-target interaction, or DTI, models take a compound and protein as input and predict some relationship between them, such as their binding affinity. They are particularly useful in the early stages of drug discovery. DTI prediction can be set as either a regression or a binary classification problem. Regression models attempt to predict continuous measures of bioactivity such as IC50. Binary classifiers predict binary outcomes, simplifying each compound-protein interaction into yes or no. Substantial amounts of potentially noisy data from different sources are required for virtual screening in industry. And binarizing continuous measures in this data using global thresholds creates essential uniformity. We have therefore developed a binary DTI classifier. We will discuss our approach to optimizing for industrial use and present results from its testing. DTI models are used in the early stages for virtual screening and drug repositioning. Virtual screening involves predicting a protein's interactions with a very broad library of candidate compounds. Drug repositioning uses DTI models for multiple proteins either to find alternative drug targets or to predict off-target interactions, since these can cause side effects. These methods are widely used for the prioritization of drug candidates. We will discuss our approaches to two problems associated with the use of DTI models in industry. Firstly, because DTI is paired data, 4 measures of accuracy result from any splitting of test and train datasets. This is analogous to cold start problems in recommender systems. The model can predict the interactions of known compounds with known proteins, unknown compounds with known proteins, known compounds with unknown proteins or unknown compounds with unknown proteins. Secondly, known protein-compound interactions are sparse, so some commonly used datasets impute negatives for unknown interactions. Additionally, compound families with high similarity are included. Together, these artificial biases mean prediction can be easy even using compound data alone. But in a real setting, models trained on these datasets would likely predict many false positives and negatives. We propose that the blind evaluation, for unknown proteins and unknown compounds, should be used as a baseline. This was not the standard previously but is the most likely case during virtual screening and drug repositioning. Since when these methods are undertaken in industry, the number of candidate proteins and drugs is far greater than the number whose interactions have been tested. To train and test our model in the most relevant way, we carefully selected 4 datasets which do not contain artificially imputed negative interactions. We then combined these datasets into a single split of test and train data according to the blind evaluation described previously. This table summarizes 2 commonly used datasets we included, as well as our complete datasets. The cross-reference mechanism of the cross-transformer encoder is the key for relating 2 modalities for the DTI task. In the cross-transformer encoder, 2 multi-head attention layers are used with source-target manner in order to refer each other. We report the baseline result for the strictest evaluation. However, We recommend that each of the 4 accuracies are reported for industrial use. Since for every query made, a user should know which accuracy is the most relevant. The PRAUC is particularly outstanding. This is of some note since it implies a particularly improved discovery of rare positive interactions. Since virtual screening and repositioning are early stages in the drug discovery pipeline, discovering true positives is more important than removing false positives. We have proposed a more rigorous and industrially appropriate method for evaluation of DTI prediction models. We have created an evaluation dataset using this idea, and by removing data biases. Thank you for listening to our talk today. We are ready to answer any questions you might have.
Okay, so yeah, any questions from the audience?
Excuse me, sorry, could you say it again?
Oh no, I'm just saying whether there's any questions from the audience.
Oh, okay, thanks.
Oh, okay, so let me ask you a question. So I think this is a very useful tool. So do you have concrete examples like what kind of drug and compound has been discovered that actually, that is effective, like the concrete examples that you have been successfully used for the field?
Yeah, so this is just on a computational model. So after developing this model, like every drug or every drug target should be tested on in the wet lab experiment, not in the like dry computation. So we have not yet, well, we have actually tested like several compounds. Like some of them are like actually hit, but this example here is just computational methods that are tested on baseline data sets. Yeah, so our contribution is like we proposed evaluation methods called like blind evaluation setup. And then we carefully created the data set. We also created a compound representation that are including the hierarchy of the compound that are not yet implemented in like graph neural network. We also created a model called cross-attention DTI. We also, yeah, cross-attention DTI is using attention neural network. Each sequence of compound and protein are like querying each other, and then that will be, yeah, producing result, like binding affinity between them.
So I see your model has like 2 transformers, right? So what's the input to each? I know one is for the source, one is for the destination, right? So how do you organize the compound and input to the transform? You have embedding first, right? So
Yeah.
Oh, okay. So you're embedding into a sequence kind of structure, then you can make it work with it. Yeah, let me see this video maybe. Yeah, so I think you have. Yeah, so here, so you have an input embedding, right? So,
Yes.
so one is a compound, one is protein. So compound is the structure that you learn the embedding for that structure. Right? So.
Yeah, so this is the whole structure of our model.
Yeah.
So we used 2 transformers at the left-hand side. At the very middle of the left-hand side model, it says cross-transformer encoder there. So 2 output from the two transformers are put into cross-transformer encoder. So in the cross-transformer encoder, there is two attention mechanisms that are represented on the right-hand side. So these two vectors, U and V, at the very bottom of the right-hand side image. So they are like two vectors as a protein and a compound sequence. And so when you query the compound sequence based on the protein, that means which part of the compound is likely to bind to the protein. And you can do the opposite thing for the protein too. You can query the protein based on the compound information. They are like querying each other, just as like query answering system in the natural language processing. And then, yeah.
Yeah, my question would be, for example, if you look at the input embeddings, right? So the output should be the tensor that can go to the transformer, but what's the input? Because the compound representation is not a sequence, right? So, yeah.
Yeah, thanks. Okay. So we first tried the Smiles representation of the compound. So Smiles representation is something like COOC, like atom-wise representation with some brackets equals that are well-known compound sequence representation. But so we modified the representation in order to include more like, include a bit more of the human knowledge, let's say. So we used the RDK function, and we used the ECFP fingerprint. So when you use the ECFP fingerprint, each atom is hashed as a unique tokens that are included. Yeah, that also represents the chiral key.
I see. So basically, you already have an encoding method that is fixed, and then you do that into another input embedding to learn the input embedding, and then go to the transformer.
Yeah. So each atom is encoded as tokens. Say a word as a natural language. Then, yeah, that is one side of the sequence.
Okay, thank you. So any other questions from the audience? Okay, if not, let's thank Kyohei for the nice talk again. And let's move on to the submission number 26. I think the speaker is Leopold France. Is Leopold here?
Yeah, can you hear me?
Yeah, I can hear you. Okay, that's great. So the title of the talk will be Deep Learning Pipeline for Patient Diagnosis Prediction using electronic health records. Let's play the video.
Hello, and welcome to our paper presentation on our paper, A Deep Learning Pipeline for Patient Diagnosis Prediction Using Electronic Health Records. I'm the main author, Leopold France, and I wrote this paper along with Dr. Yash Raj Theta and Dr. Bibek Paudel. Multimorbidity. Multimorbidity is a growing problem in our society. On the one hand side, our general population is aging quickly. On the other side, we're also seeing a general increase in the prevalence of multimorbidity. So more people are more frequently affected by multiple long-term or chronic conditions. As a result, we're seeing a high increase in people that are affected by multiple diseases that need to be accounted for. All these long-term conditions need to be correctly diagnosed. Currently, a recent paper has shown that multimorbid patients are underdiagnosed 71% of the times by doctors. Our solution is to provide a data analytics solution that analyzes EHRs and then, using deep learning algorithms, provides doctors with support to correctly diagnose all conditions. Now, let's have a look at the related work. As you can see, I've chosen 5 papers. 4 of them are also diagnosing diseases, most of the papers that diagnose diseases solely focus on one disease, the main disease, for example, or on a particular disease, for example, only diagnosing diabetes. Now, some of the papers here in this list, as well as our paper, tries to diagnose all conditions simultaneously that a patient is affected by, therefore allowing the treatment to be targeted and optimized for what conditions the patient has. Furthermore, I've also added the clinical BIRD paper that we have built up upon for our unstructured data in the EHR dataset. There are three main areas to data-driven methods. The data, how good is the data, the quality of the data, how well was it recorded? The representation of the data, how well was it stored, and how well is it represented to be able to learn from it? And thirdly, how good is your algorithm that can learn from the data? Is the algorithm interpretable? Can it explain certain decisions it takes? It's a data set from an intensive care unit of a Boston hospital in the US. As part of this paper, we have transformed the MIMIC3 dataset into an FHIR format. This FHIR format is called the Fast Healthcare Interoperability Resources format. It's presented by the Health Level 7 international nonprofit organization to establish a baseline disregarding of the country so that we can share data more easily. To this end, we have made public a Python package that you can use to transform the MIMIC3 dataset into the FHIR resources format. Here you can see the GitHub repository that we provide the link with, and you can also see the table of the MIMIC3 tables and how they are mapped to FHIR resources and to which resource types. As part of our paper, we provide two deep learning models. One that analyzes structured data. We have named this model the Deep Observer model. We first pre-process the data, and then using multiple neural network layers, convolutional network layers, and fully connected network layers, we process any structured data. So these are vital sign measurements from the chart events table that we then analyze to make predictions for the certain diseases. In the MIMIC3 dataset, we can find ICD-9 disease diagnosis codes. As there exist so many disease diagnosis codes, these ICD-9 codes, more than 15,000, we have mapped these 15,000 disease codes to 281 meaningful CCS categories. And then for each CCS categories, our model outputs a certain probability that it believes this admission will be assigned with an ICD-9 code from this CCS category. The second model that we propose analyzes unstructured data. We named this model the Clinical BERT Multimodel. Again, we pre-process the text as the unstructured data in the dataset are the doctor reports. Pre-process these texts, convert them to tokens, adding a certain classification token, running these tokens through the revolutionary NLP BERT algorithm, but only the transformer encoder part. Then we pass the encoded classification token through to another extra classification layer, and then again receive an array of probabilities for each CCS category whether this admission will be diagnosed with an ICD-9 code. On to the metrics. How do we evaluate how good our model is performing? There are two main figures that we can have a look at: the receiver operating characteristic curve and the precision recall curve. Popular metric is the area under the receiver operating characteristic curve. Furthermore, there's also the area under the precision recall curve. Additionally, the recall at precision 80. This metric corresponds to how high the recall is when the precision is at 80%. To compare the different models that we have developed in our paper, we'll use the AUPR, as the AUROC score is actually not very representative of a score for very unbalanced data sets. Most of the admissions in our data set have negative labels for most of the diseases. That's why it's a very unbalanced data set. The AUPR score is a more accurate and more representative metric to compare these unbalanced data sets. All right, let's have a look at the results. Now, first step, we'll compare what first layer for the deep observer model, the model that looks at structured data. We've transformed this vital sign data into admission representations of 4 time steps. And so this first layer transforms these 4 time steps and tries to identify patterns from it. And so what we've tried is that we've tried a fully connected neural network layer, or a convolutional layer, or a recurrent neural network layer. And so comparing the performance of these different layers for the first layer of actually the deep observer model, we can see that the convolutional neural network layer has worked best looking at the AUPR score. Now, as a second experiment, we verified that the more information that the model gets. So here we compare the clinical bird multi-model or the clinical bird binary model when feeding these models with the reports from the first 2 days compared to the first 3 days. And we can see that every time the model improves when it receives more data and also receives the data from the 3rd day of the admission. As a third task, we then try to compare if a model that's solely trained on one diagnose category performs better than models that are trained to diagnose all disease categories simultaneously. For that, we have trained the clinical bird binary model that is trained solely to predict CCS category 98, corresponding to high blood pressure. And so what we can see is that this model actually outperforms the clinical bird multi-model or the deep observer CNN model that predict all disease diagnoses, so these CCS categories simultaneously. Now, the last and overall performance of the model, we look at the models that predict all CCS categories simultaneously. We also loosely compare the models that we have developed with a model that developed by the Google paper mentioned in the related work that actually predicts all ICD-9 codes simultaneously. This task that they have is slightly more difficult, explaining also their lower performance. But what we can see from our models is that actually the clinical bird multi-model that predicts the CCS categories simultaneously using the doctor reports from the first 3 days performs best. This can maybe be explained that there's more reports and actually more information from the first 3 days compared to only looking at the discharge summaries when looking at the discharge task. That's only looking at one report instead of all the reports from the first 3 days. As an additional benefit, the clinical bird models can also be interpreted to a certain extent. What we can actually do is we can visualize the attention layers in these transformers from the BERT NLP model. We can visualize these attention layers to see which tokens the model has put a lot of weight on, and so which it has focused more, where it has put its attention. And so here, for example, we can see that the failure token has been critical to diagnose which conditions are diagnosed. Now, onto the limitations of our model. As one of the major limitations that we have is that we only use data from one department, from one hospital. What we'd like to do in the future is augment this data set from data from other hospitals, also converted to the FHIR format, this international data format. Furthermore, we need to make sure that our model is accepted by doctors and in practice. What we need to do there, and what helps there, is to show them that our models can be interpreted to a certain extent, like the clinical bird multi-model, where the deep observer model would need to add, we would need to add more interpretation there. Next, we also need to make sure that the model is not biased towards certain people and is as ethically correct, as this can impact a lot of people simultaneously if adopted. Furthermore, a difficulty with our model is that even if we are able to diagnose all these conditions simultaneously, little is actually known out there on how to treat multimorbid patients. So this is definitely an area where more research needs to be done to find out how these patients need to be treated properly. All right, so this was the presentation for our paper. If you have any comments or questions, please feel free to reach out to us. You can find our emails in the paper. You can access the paper through the QR code or through the link below. Thank you very much.
Oh, thank you, Leopold. So any questions from the audience? Okay, I have a question about the FHIR, right? So there's a data format, right? So what is the features of the data format right now? Like, it seems that you want to make it like a standard that every, let's say, hospital, they can export the data into this format to ensure some properties that people can safely share the data. Yeah.
Yes. So the FHIR format is a kind of a healthcare data format that is trying to like establish itself, and it is already quite popular in the US, especially as soon as the hospitals share data in between, themselves. They use this. They mostly use this FHIR format, and it's also starting to become popular here in European, where I'm here in Switzerland. So it's also starting to get popular here, and they're trying to, the different hospitals, I know different hospitals, they're starting to implement this kind of connection access point where they can then transform the data they have in their database first into the FHIR format and then kind of share it with other hospitals.
I see. So there's a certain like mapping of different entries, right? So besides this, do you have like anonymization features like there so that people can share easily?
Excuse me, I did not understand you.
So like, is it just a way of exchanging the data, or is there any privacy protection for the data format?
There is, so for the data, you still need to encrypt it, and with the Health Level 7 organization that proposed this format, actually has multiple kind of different areas. The FHIR is kind of the data format and how it should look like, but there's also kind of the whole exchange of how the data needs to be exchanged. And I haven't really looked into the privacy side and how the data actually gets exchanged.
Got it.
I was focusing on the format.
Yeah, basically you say that if people want to anonymize the data, they should do that before and then convert to the data format. Right?
Yeah, I mean, you can, yes, you can anonymize the data beforehand, and depending on who you're sharing the data with, you maybe don't need to share, you don't need to or anonymize the data, right?
I see. So the second question would be this. So I see that you have the EHR data categorized into two categories. One is really the reports, right? The natural languages, so you can admit to the transformers, I think the BERT, right? So BERT model. The other is more like a traditional structured database data, right? So why you want to use a convolution for this structured database data? Because to me, convolution means that all the attributes are kind of homogeneous, right? So whether it's pixels, whether it's time series, or it's kind of the same type, do not need any scaling, right? So then otherwise, potentially for traditional data, like the support vector machine, those kind of model may achieve better results. Right? So I'm not really sure. So maybe you can comment a little bit on this.
So for the structured data, we use for this structured data, we use kind of a similar pre-processing steps as the Google model did. And that's why we kind of grouped it into only 4 time bins, similar to this other paper. And so because there are only 4 time bins, I tried with the RNN model, but it's not a lot of time steps that you can really learn like temporal patterns from. And so actually the CNN, the convolutional part, we actually only use a filter across the time dimension, which only has data for the same I was only trying to recognize like temporal kind of patterns for each of the kind of different measurement types, I would say.
I see. So these are not the time series data, right? These are the attributes for patients. Right? These are not like EEG or something.
There's also EEG. So the time data was converted into like grouped into like 4 singular time bins. So in total, there are 281 different kind of measurement types. For example, the heart rate or the glucose level, different the blood pressure, and so this data was then grouped into, so each kind of measurement was then grouped into these 4 time bins, and these correspond to like the last 8 hours of the admission, the 8 hours before that, and the 8 hours before that, and then the between the last 24 hours of data and the beginning of the admission, the whole data was then grouped into the last time bin. So we have a resulting kind of matrix that has a size 281, the number of measurement types, and the 4 time steps, kind of the more 4 time bins, kind of representing the temporal kind of side of the structured data. And so with what the convolutional layer does is then it kind of maps down this temporal pattern to a single and tries to identify patterns across this temporal kind of side of things. And so then at the end we get a resulting like a resulting array of this of size 281 and the number of channels that we have for the convolutional, which is 256, I believe. Otherwise, you can look this up in the paper to be sure.
Okay, thank you. Any other questions from the audience? Okay, if not, let's thanks Leopold for the interesting talk. And
thank you very much.
You're welcome. Let's move on to the, oh, so just one, I think I need to. Okay, so next talk will be given by Just Wang. Is Just Wang here?
Yes, I'm here.
Okay, thank you. So the title of the presentation would be MGATRX, discovering drug repositioning candidates using multi-view graph tension. Let's stream the talk, please.
Hi, my name is Jaswant Yella, and I'm going to be presenting our work on MGATRX, a multi-view graph attention-based drug repositioning algorithm. This is a joint work with Professor Anil Jacob. To give you some background on the problem we are presenting, the drug discovery process in the United States undergoes 3 critical stages, where numerous compounds are evaluated to pick the right one for a given disease. This also includes many phases and steps within each stage for FDA to approve the final drug. As per an estimate, the total average cost for developing a new drug from discovery to approval ranges from $2 to $3 billion and takes about 13 to 15 years. To bypass this conventional slow and cost-intensive procedure, computational approaches are increasingly used to identify new therapeutic uses for existing drugs. The ideal rationale being drugs approved by the FDA or those currently in late stages of clinical trials have known safety and toxicity profiles. Thereby, in silico methods are found to be resourceful and time efficient. This strategy, in which new indications are identified for existing therapies, is referred as drug repositioning, and hence candidate repositioning drugs can enter clinical phases more rapidly and at a relatively reduced cost. Provided the background, the problem we are trying to solve is as follows. A drug disease-oriented multi-view heterogeneous network consists of different node types such as drugs, side effects, targets, diseases, medical subject terms, and drug substructures. Given this network as input, the goal is to learn and identify missing associations between a drug and disease. Our motivation being to identify new uses for approved and investigational drugs that are outside the scope of the original medical indication. To approach this problem, we consider some of the baseline models which are proposed for multi-view bipartite networks. LRSSL is a matrix factorization-based model proposed by Liang and others in 2017. In this study, we retrieved k-nearest neighbors by calculating cosine similarity of the drug annotation profiles, and then use Laplacian regularized sparse subspace learning to identify reproportionable candidates. In graph neural network-based methods, NeoDTA proposed by Van and others in 2018 learn node-level embeddings and predict drug target associations, which, however, we extended for drug disease associations. HNRD from Wang and others used NeoDTA algorithm for drug disease association problem. However, they apply their model on drug-drug similarity and disease similarity networks. MedGCN from Mao and others proposed in 2019 used graph convolutional network for multi-view bipartite networks for patient medication recommendation problem. The proposed algorithms have few limitations. The similarity-based approaches were evaluated with an underlying assumption that nodes sharing similar annotations have similar associations. As a result, latent representations generated through similarity networks may not necessarily capture the complex relation of drugs and diseases. Additionally, similarity-based approaches do not consider missing information. Several drugs and diseases, for instance, have missing information and therefore are not considered. For example, drugs and diseases tend to have off-target or indirect effects either through protein interactions, signaling networks, or pathways, which are not typically detected in preclinical drug discovery stages, leading to poor predictive performance. Most of the proposed methods lack understanding of the molecular basis for the drug disease predictions. Since the annotation profiles are collected from various data sources, even with manual curation, some of the noise in the neighborhoods is inevitable. Current algorithms lack the ability to filter the useless information in the node neighborhoods while learning embeddings. In this slide, we further discuss how aggregation mechanisms are important in learning node embeddings. The graph convolutional network proposed by Thomas Kiff and others performs localized first-order approximations of spectral graph convolutions, which is primarily proposed for single-view homogeneous networks. Here, each node embedding is based on weighted sum of its neighbors' embeddings. MedGCN extended it for multi-view networks for patient medicine recommendation problem. However, the quality of annotation varies across views, which can potentially affect the aggregation mechanism. For example, let's consider a sample subgraph of a simvastatin network. Its first-order heterogeneous neighbors would be targets such as HMGCR and ITGAL, side effects such as rhabdomyolysis, mesh-term hypolipidemic agents, and let's consider one of the simvastatin indication, that is hypercholesterolemia. Simvastatin node learns from its neighbors, where the inbound red line indicates that the node is learning from its immediate neighbors, while their immediate neighbors will learn from their neighbors, that is nodes such as HMGCR, hypercholesteremia, hyperlipidemic agents, rhabdomyolysis, and so on from others. The ultimate task for a given unknown disease is to predict the missing link between the drug and disease. Biomedical and genomic data tend to be relatively sparse. Therefore, it is important to assign varying importance to different neighbors while predicting a link between a drug and disease. Hence, we approach graph attention-based approaches. In previous slides, Velikovic and Tecumseh used attention mechanism for aggregation mechanisms. Tecumseh proposed similarity-based attention, where relevant neighbors that share similar representations are given more attention according to their contribution. For given two nodes, I and j, the attention from node j to node I is calculated as follows, where hi, hj are the node embeddings of node I and j. In other words, attention alpha ij is obtained by multiplying a trainable scalar parameter beta to the cosine similarity of the embeddings, followed by applying a softmax function. Hence, the nodes should be able to attain relevant information from their heterogeneous neighborhood, filtering out any useless information for predicting association for a given disease. In MGAT-RX, we extend the attention to multi-view networks, and the intuition is formulated as follows. First, we have the following views: drug disease view, target view, side effect view, substructure, and mesh view. Next, from the disease annotation data, we have disease target view. We can see that target colored in green is the most common annotation space for both drug and disease. Here we have 5 drug views and 1 disease view. Given this multi-views, for each adjacent matrix in the view, a linear transformation is applied. This results in embeddings for each view. Here, each embedding is denoted according to the node type color, H0, H1, H2, and so forth. The attention is computed such that first, attention is computed within the view, that is, embeddings for the drug nodes are updated based on the drug-drug attention. Then attention is computed across the view, that is, embeddings for the drug nodes are updated based on the disease attention. Similarly, embeddings for drug nodes are based on target, side effect, mesh, and substructure. This procedure is performed similarly to the disease, where it learns from within the view and across the views, such as drugs and targets. Note that here target is a common annotation space for both drug and disease. This way, orphan diseases and investigational drugs can learn representations, even if the neighborhood is extremely sparse or unknown. Similarly, we can see procedure for target, side effects, substructure, and mesh annotations. This layer we refer as multi-view graph attention layer. We formulate the multi-view attention layer similar to the single-view attention. This way, the node embeddings in the views are updated simultaneously. These node embeddings can be further used for downstream classification tasks. In this work, we use drug embeddings and feed them into a single linear layer. We then perform multi-label classification, where a value between 0 and 1 suggests the probability of having an association between drug and disease. For predicting drug-disease association, we calculate binary cross-entropy error of drug-disease association prediction and reconstruction error of the remaining views using mean squared error. The collective loss for MGAT-RX is given as follows. The proposed framework and algorithm is applied on curated set of drugs, diseases, and their annotations compiled from various sources. Most of the previous works for identifying novel drug-disease associations evaluated their performance using a dataset curated in 2014. However, since 2014, several new drugs have been approved. Just alone in 2018, the FDA approved as many as 59 new drugs. We manually curated our dataset from multiple sources and constructed a multi-view heterogeneous network with a compiled list of 3,167 drugs, 1,620 diseases, close to 10,000 targets, approximately 11,000 side effects, 1,661 medical subject terms, and 881 substructures. In this table, we show the views along with their sizes, edges, and the sparsity of the networks. In our experiments, we performed 10-fold cross-validation, comparing it along with the baseline models presented previously. We use the traditional evaluation metrics such as AUPR, AUROC to quantitatively evaluate and compare our method with the existing baseline models. Our comparative analysis with 4 current state-of-the-art models shows substantial improvement in prediction performance. This shows that MGAT-RX can handle extremely sparse networks. To test the argument that our proposed attention model is robust and convolution-based method, we removed a fraction of edges and compared the performance. In this figure, we show the robustness of MGAT-RX and MedGCN by removing 15, 13, 45, 60, and 75% of edges. Our proposed algorithm performs substantially better than MedGCN in robustness test, despite removing edges from the training and evaluated with test set. Evaluation and comparison of MGAT-RX with current state-of-the-art models show that MGAT-RX is superior in terms of all the metrics. The performance of MedGCN is inferior when compared to MGAT-RX, suggesting that attention helps in exploiting higher-order neighborhoods in multi-view networks. Attention mechanism over multi-views learns which neighbors are more relevant and weighs their contributions accordingly. The comparison test also indicates that attention is robust and able to perform well with limited data in predicting associations when compared with convolution-based approach. To visualize the impact of attention on the model, we selected immunological disorders such as asthma, psoriasis, Crohn's disease, and chronic ulcerative colitis. We selected few of the top predicted drugs for each of these diseases based on the drug diseases attention weights. Next, we filtered 15 targets which are shown to have maximum attention from these drugs and diseases. Here we show the drug target and drug disease target attention heat map. The highlighted values in the heat map show how much attention a target gene is contributing for constructing drug and disease representations, which further aids in predicting association between a drug and a disease. We selected the highlighted attention targets showed in the heat map for chronic ulcerative colitis and then used top gene suite to identify functional enrichments for biological processes. We found that these genes are enriched for inflammatory response and regulation of immune response. This probably explains the presence of immune suppressive agents among the top hits for these immunological disorders. We further discuss such similar examples in our paper. We extract the drug representation in the decoding layer and apply t-SNE to further identify hidden patterns. Here we show the cluster of drugs color-coded according to their ATC codes. The visualization also reveals potential promiscuity patterns of drugs such as alimentary tract, anti-infectives, cardiovascular drugs. These overlaps also suggest there's a drug repositioning potential. In our work, we briefly discussed some of the novel predictions of MGAT-RX. We selected 12 drugs with their original indication and MGAT-RX predicted indication, along with the literature evidence for ongoing investigations. Most calcium channel blockers are known to have therapeutic efficacy for hypertension. In our predictions, a couple of calcium channel blockers in clinical trials are predicted for high blood pressure. Dextroamphetamine is a well-known drug for treating narcolepsy and attention deficit hyperactivity disorders. In our predictions, we found that it is predicted to treat obesity. To conclude this presentation, we summarize our works as follows. By integrating drug-centric and disease-centric annotations as multiviews, we propose a multi-view graph attention network for indication discovery. Unlike most current similarity-based methods, we employ graph attention network on the heterogeneous drug and disease data to learn the representation of novel nodes and identify associations. MGAT-RX outperformed 4 other state-of-the-art methods used for computational drug repositioning with an up-to-date drug association data. Besides, we also visualized the learned attention for select drugs and disease groups to enable understanding for the molecular basis of the drug disease predictions. Several of our predicted drug disease indication pairs overlap with drug indications that are either currently in clinical trials or are supported by literature references, demonstrating the overall translational utility of MGAT-RX. Lastly, but most importantly, in support of reproducible research, we make all the MGAT-RX data and source code publicly available at GitHub. Thank you for taking time to listen to this presentation. Please let us know if you have any questions. we are more than happy to discuss. Thank you.
Yeah, I really like this work. I wonder if you tested and know some limitations or weakness to your approach. As you mentioned that all the novel ones are already been validated in literature. For the truly novel one that hasn't, have you looked at them and talked to clinicians or biologists, or you're determining whether it's a literature is falling behind on your discovery, or there's probably some errors?
Yeah, so like we still haven't like discussed with any biologists, but couple of drugs like dexamethasone for IPF, which was actually being investigated in one of my advisors' collaboration lab. So like not every drug has been like individually evaluated whether they are feasible for repositioning.
Oh, okay, thank you. So any other questions from the audience? Let me see. So let me ask you a question. So what's the major gain? Because I see that you also have MAD GCN, right? So which means there are people already using graph neural network, right? So I think the main contribution that you have is you have a hexapeptide peptide graph, right? So and then I think maybe it's the way that you do the GAT on different parties, right? So let me see which slide you. I think it's somewhere here.
Evaluation and comparison.
So I think it's just not following.
Similarly to the disease, where it
I think it's this part, right? So, so why is this way of doing attention much more effective? Because from my point of view, it's really you are having all the combinatorial possibilities of every pair of like a connection being examined, right, between every pairs. What's the difference from this method compared with, for example, just simply treat them as all the same kind of node and just like a ordinary JT? What's the difference?
GCN.
Yeah, so the attention, because there's a model called JT, right? So graph attention network.
Yeah, so we are using the, so in the previous slides, I mentioned about the Velikovic's graph attention model, and then there is Thickham-Parampil's work on graph attentions, which were primarily proposed only for homogeneous models. I mean homogeneous networks. So here mainly the Thickham-Parampil work, which considers the fact that like the embeddings which can be actually computed, like basically you take the any similarity through dot product or like cosine similarity, and and applying a softmax on top of it will give the attention. So inspired by that idea of like we basically extended that on top of multi-view networks, where especially like multi-view in a sense like is a heterogeneous network, like, and we try to like compute attention within the same node neighborhood and across the different types of node types. And so in that way, like when compared with the graph convolutional approach, which basically aggregates like the first order neighborhoods and extends so forth. So it substantially performed better than the attention based model.
Oh, okay, thank you. Any other questions about the work? Okay, if not, let's thank Jaswant for the interesting talk, and let's move on to the next one. So Ning Wang is a presenter. Is Ning Wang here?
Yes, Dan, I'm here.
Okay, thank you. So the title of the next talk will be Explainable CNN, Explainable CNN Attention Networks for Automated Detection of Alzheimer's Disease. Let's stream the video first.
Hi everyone, I'm Ning. Thank BIOKDD for providing us this great opportunity to present our recent work on automated detection of Alzheimer's disease. We propose novel explainable CNN attention networks, which is done in collaboration with Professor Subal and Minxuan in Stevens Institute of Technology. Alzheimer's disease is a serious and high-cost mental health issue globally. In US, more than 5 million individuals are living with Alzheimer's, and Alzheimer's and other dementias will cost the nation $305 billion by this year, and the number is rising up to $1.1 trillion by 2050. However, studies have shown that early diagnosis and intervention can delay the onset. Traditionally, biomarkers tests on brain images and protein in cerebrospinal fluid are highly used, but those tests are normally expensive, complex, and not always available. As a result, other substitutes are emerging, like cognitive and memory tests. Based on participants' performance score on each task, their dementia status would be measured. Another popular way is using linguistic tests. Participants would be asked to use their own words to describe a picture. Then the diagnosis will be made by analyzing on their language ability on the description. In addition, some studies have created high-quality data sets for the recorded descriptions along with the corresponding converted scripts, like Optima and Dementia data sets. Thank you so much for that. We are now able to use cookie shift subdataset in Dementia Bank to train and test our models. Our major contributions in this work are: we designed novel explainable deep learning architectures for early detection of Alzheimer's disease. We provided inter- and intra-feature attentions to capture relative importance between the different feature classes and the relevant importance of features within a class. And also, we provided explanation of the model's conclusions. In addition, our modular architecture that can be extended to as many feature classes as desired. We did extensive testing on the Dementia Bank corpus. Last but not least, we provided example explanations using the proposed models. We proposed 3 models in this work. They are C-attention FT network, C-attention embedding network, and unified C-attention network. We can see in the left figure, we have 2 independent networks. Each network trains on one class of features. The 2 networks are very similar, with a slight difference due to the characteristics of feature classes. We will get to that soon. In the left figure, the left leg presents the architecture of C-attention FT network. In the architecture, we use part-of-speech features only. I will explain the feature details in next slide. Part-of-speech features are fed into 6-layer self-attention network. Each of them is followed by a feed-forward network. Then we use another self-attention layer to extract the feature importance based on the attention value for each feature. Then a single convolution layer is applied to capture the most important feature per filter. After a softmax layer, we generate the final decision of Alzheimer's detection. The right leg shows the architecture of C-attention embedding network, who uses sentence embedding features. The architecture is very similar to C-attention FT network, but has an extra positional encoding before the self-attention in order to memorize the input order of each sentence. But why we need position encoding in C-attention embedding network, but not in C-attention FT network? The attention network in our architecture has no recurrence, but in order to use the sentence embedding features, we need to know the position and order of each sentence in the attention embedding network. While on the other side, POS features don't have the position information. That's why we can omit positional encoding in the attention FT network. The red figure presents our unified C-attention network. We concatenate the output of previous two models and feed them into another attention layer, followed by a dense layer to generate the feature importance in interclass level. Like other two networks, the final decision is made after a softmax layer. Here are dataset and features we use. Like I've mentioned already, we use cookie shift subcorps in Dementia Bank. This subdataset contains transcripts of the description of a picture showing the shift of cookies. 1,049 transcripts from 208 AD patients, 243 transcripts from 104 control individuals, total of 1,229 transcripts. And the feature we used two classes of features. First, part-of-speech features. POS tags are generated by using famous NLTK package, and another is the latent features. The universal sentence embedding is used to represent each sentence in a speech record. USE is a pre-trained sentence embedding model provided by Google. In our experiments, we compared our work against the latest state-of-art benchmark in terms of accuracy, precision, recall, F1 score, and area under the curve. Our method outperforms it with an accuracy of 92.2% and F1 score of 0.95. In our works, overall performance is achieved by both the proposed C-attention FT network, which use POS feature only, and unified C-attention FT embedding architecture, which trains POS features and latent features separately on each C-attention network and unified the result by another attention network. And more specifically, the C-attention FT network performance best in terms of accuracy and F1 scores, and the C-attention FT plus embedding performance best in terms of precision and AUC. In this work, we also provide multiple explanations. First, explanations using latent features. In this table, we provide two records in the test dataset. Label 0 indicates that the description was ordered by a healthy individual, and label 1 indicates that the description was ordered by a patient. In each of those examples, the unified C-attention FT embedding network classified the orderings correctly. The column important sentences refers to the sentences that are captured by the sentence attention and 1D CNN layer, which indicates higher importance of those sentences. In record number 1, we can see that the sentences, I would like to have a lead pencil. I would say that because we have a daughter who is pregnant. Those are sentences which are not related to the scene in the picture, and along with pauses in the description, are used as most important sentences for identifying this speech belongs to an AD patient. The same logic applies to the second record as well. The little girl is reaching for a cookie. With gravity, he's going to fall on the floor because of the stool's knot. Are the top 3 most important features in the ACE detection for this record. Second, explaining the role of part-of-speech features. The following part-of-speech features are the most important part-of-speech features overall in entire dataset. An MPS, who stands for pronoun, makes up 42.6%. MD, which stands for model, makes up 14.3%. EX, who stands for extension, makes up 14.1%. PRP, who stands for personal pronoun, makes up 9.9%. And for more detailed explanations of those features can be found on our paper. We can see that the noun and pronoun features contribute highly to the detection, which means the model highly depends on the value of those features to make a decision. From the conclusion, we can see that our findings are consistent with previous works that AD patients tend to change usage of pronouns and nouns compared with healthy controls. More specifically, they tend to use more pronouns than nouns. And last, explaining the relative importance of feature classes. From the pie figure on the right side, we can tell that part-of-speech features seem to play a more important role than latent features in detecting AD, as it contributes 65.1% to the final decision overall. This finding is consistent with our performance metrics, which shows that overall, the C-attention FT network performs better than the C-attention embedding network across multiple terms. At the very end, I would like to conclude this work as follows. We proposed 3 explainable architectures using CNN and attention to detect Alzheimer's disease using 2 kinds of features, part-of-speech and language embeddings. Our C-attention models outperform latest state-of-art deep learning models by reaching an accuracy of 92.2% and F1 score of 0.95. C-attention FT architecture performs best in terms of accuracy and F1 scores. And the C-attention FT embedding performs best in terms of precision and AUC. While at the same time, our models are able to generate explanations of the action of the AI by using attention layers and 1D CNN layer to capture explanations at 2 levels, one each at the intra-feature level and the inter-feature class level as well. And that's the end of my presentation today. Thank you so much for listening.
Okay, thank you, Inwang. So let's have the Q&A. So any questions from the audience? Let me see, there are 2 chat. Okay. Okay, so let me ask you this question. It's interesting to know that actually the part-of-speech features are more important than the language embedding, right? The sentence embedding, like the traditional machine learning models for NLP, like the BERT exam model. Is it because of the specific scenario, like Alzheimer's disease patients tend to like swap the words or like using pronouns more than nouns? That's the habit of the formulating the language is a major detector for this disease. Yeah, so that's my question.
Yeah, it could be. So in previous works, actually multiple works proved that the Alzheimer's disease, the patient of Alzheimer's disease may have the tend to use more pronouns than nouns. They sort of lack the ability of using the specific words. That's the reason. That could be one reason why part-of-speech feature plays more important role than the latent feature.
Yeah. So for the part of for the post features, do you mean that for the sentence for each word you just get a post label, and then you still have this post sequence that enters, or you don't have the position formation? How do you extract the feature, or is it like the proportion of pronouns or nouns? I mean, how do you define the post features here?
Part of speech feature is just to count the number of the different kinds of word.
I see. It's a frequency.
Yes.
Okay. Thank you. Any other questions from the audience? Okay, if not, let's move on to the next talk because I have a class to teach very soon. Okay, so the last speaker is Jay Lee Zhou. Is Jay Lee here?
Yes, hello.
Oh, hi.
Both Bao and I will be answering question later. So.
Oh, okay, thank you. Yes, good to know. So the title of the talk is SODA, Detecting COVID-19 in Chest X-rays with Semi-Supervised Open Set Domain Adaptation. Let's stream the video first.
Hello, everyone. My name is Jie Li Zhou, and today I will present our work SODA, Detecting COVID-19 in Chest X-rays with Semi-Supervised Open Set Domain Adaptation. It is the joint work with my colleague Bao Yujing and Zhe Yawang. A little bit of context. WHO declared COVID-19 as public emergency of international concern on January 30 this year. 6 months later, COVID-19 has infected more than 17 million people and taken away over 670,000 lives. By far, the most reliable diagnosis is through viral testing, or RT-PCR. But there are limitations for viral testing. First, aerosol pathogens could be released and will put the healthcare workers at great danger. Second, testing process takes a long time, ranging from a few hours to days, and large volumes of tests have already drained lab resources, as observed in many states across the United States. Third, recent study reports that the sensitivity of RT-PCR is around 60 to 70%, while the sensitivity of chest radio imaging was promising at a higher rate of 97%. Due to these limitations of viral testing, chest radiology has already been used as a complementary screening process in many countries. It not only is more widely available, but has a much faster turnaround time. Furthermore, chest imaging provides many more details about the patients. For example, the pathology location, the lesion size, and the severity of lung involvement. This valuable information can better help with prognosis and further help doctors to triage patients into different risk groups. Recently, we observed that many deep learning-based chest imaging tools have been developed for detecting COVID-19. To give a recap of these methods, we observed that many recent works first train a convolutional neural networks on existing large-scale and clean chest X-ray image dataset, and then fine-tune it on a much smaller COVID-19 dataset consisting of noisy images. Fine-tuning-based transfer learning will cause overfitting issues because it ignored the visual domain shifts between the two datasets, and the trained model loses the ability to detect common thoracic diseases like effusion and nodule, since these labels simply do not appear in the new dataset. To address these two limitations, we propose semi-supervised open set domain adversarial network, or SODA, to tackle this. First, we define the problem in a domain adaptation setting, in which the source domain is a large NIH chest X-ray dataset, and the target domain is the smaller COVID chest X-ray dataset. Pneumonia is a shared common label across these two datasets. Then we first align at the domain level. Domain adversarial training is the most popular method for helping feature extractor learn domain invariant features, such as a model trained on source domain can be easily applied to target domain. However, such a practice ignores the label structure across domains, which will result in false alignment and even negative transfer. As shown here, labels are all mixed together. To address the problem of false alignment and improve the knowledge sharing across domains, we further propose a novel common label alignment mechanism. Common label alignment aims to mix the image distribution of common label across domains. As shown in the red box here, the common label alignment mixes images with common label pneumonia. Such a practice avoids a false alignment between pneumonia and other diseases like infiltration and cardiomegaly. Besides, our experiments show that common label alignment also helps to distinguish COVID-19 and the common pneumonia in the target domain. Here, we present the overall architecture of SODA, which comprises of 4 parts: feature extractor GF, label predictor GY, domain descriptor DG, and our 2-level alignment component consisting of common label discriminator DC and common label recognizer R, which each of them will have probability, outputs, and losses. So during training, first, GF, which is a CNN, extracts hidden features H from chest X-ray image. H will then be fed into multi-label classifier GY to predict the disease probability. H will also be fed into adversarial domain discriminator DG and DC to get the probability that it belongs to the source domain or the target domain. And the common label recognizer R will produce the probability that the image is associated with a common label or not. Our key innovation in SODA as compared to other domain adversarial networks is the 2-level alignment component. Firstly, the general domain level alignment, H, the hidden feature extracted from the image is adversarially trained using general domain discriminator DG as shown before. But this will mix image features from source and target domains while destroying the label structure, which will cause the false alignment issue. Secondly, the common label alignment process, in which it will only backpropagate weights for images in the common label set, in our case, the pneumonia. Specifically, we use recognizer R to predict whether a chest X-ray is associated with a common label pneumonia or not. For experiments, we use chest X-ray 14 datasets, which have 112 K well pre-processed and annotated images covering 14 common thoracic diseases. We then use the newly available COVID chest X-ray dataset as our target data domain. By the time of the project, it has 328 images from various public sources, such as online publications and online repositories from different hospitals around the world. We follow the semi-supervised training protocol, where during training, we only use 40% of the label images in the target domain, while evaluation is done on the rest 60% of the image. We compared 5 models in total, 2 groups of model. First is fine-tuning model like ResNet 50 and DensNet 121. And also like domain adaptation models, recent state-of-art models like DNN and PADA. We run each model 3 times and report the average AUC ROC score. In this table, we observe that fine-tuning based models have lower performance than domain adaptation models, and SODA outperforms recent domain adaptation models in detecting COVID-19. To further evaluate the length hidden features, we computed PAD, or proxy A distance, which measures the feature distribution discrepancy between the source and target domains. In general, a lower PAD means a better ability of the model for extracting domain invariant features. We can observe that SODA has a lower PAD compared with the baseline domain adaptation methods, which indicates the effectiveness of our proposed 2-level alignment strategy. We then use TSNE feature visualization to visualize the hidden features extracted from domain adaptation in a 2D space. In this graph, the red points corresponds to pneumonia, while the blue points corresponds to COVID-19. We observe that SODA outperforms the other 2 domain adaptation models in separating COVID-19 from chest X-ray. We can see a clear separating line here. And finally, we use GradCam is used to visualize the features extracted from all compared models. These images have annotations arrows indicating the pathological locations. We observe that ResNet 50 and DensNet 121 can focus wrongly on irrelevant locations like the dark corners and the edges. In contrast, domain adaptation models seem to have better localization in general. And our SODA model gives more focused and accurate pathological locations than other models compared. In addition, we consulted an experienced radiologist from Wuxi People's Hospital in China and received initial positive feedbacks on the pathological locations as found by SODA. In conclusion, in this project, we propose SODA, a novel deep domain adversarial neural network, which can better utilize the large available labeled chest X-rays for small set of COVID-19 images. In practice, we believe SODA can be generalized to other medical imaging problems where there are large, well-annotated datasets and smaller, newly available datasets. Overall, SODA can serve as a pilot study in using domain adaptation methods for radiology imaging classification problems. Thank you.
Okay, thank you. Any questions from the audience? Okay, let me ask a question. So how do you define the loss function because you have so many modules, and how do you train the model? Could you shed light on this point? Hello? Jelly, can you hear me?
Okay, hello. Hi, this is Baoyu. I'm a co-author of the paper.
Sorry, I was disconnected a moment.
Oh, no worry, yeah. Okay.
Yeah, I mean, either Baoyu or I can answer your question. Yeah, Baoyu, go ahead.
Yeah, so basically we have two parts. The first part, as shown in the blue part, this is a label predictor. So for the label predictor, the loss function is the cross entropy between the predicted label and the ground truth label. For the other parts, like the DC and DG, these are the domain discriminator. So the label for the domain discriminators are the domain label, because we know from the training set that which image is from the source domain, which is from the target domain. So the loss function for the right part is this cross entropy between a ground truth domain label as well as the predicted domain label. And for the yellow part, the R is a common label predictor because we, in our model, we do a domain alignment at the common label level. So the common label recognizer predicts the label, predicts whether this image contains the common label, like the pneumonia or not. So the loss function for R is also the cross entropy between the ground truth, ground truth label and with the predicted label. So the final loss function is a linear combination of all of these three parts.
Okay, thank you. Any other questions from the audience? Okay, if there's no more questions, let's thank Jelly and Baoyu for the cool talk. Okay, so so that's the end of session 3. Session 4 will begin, I think, 8 minutes later because I have to teach a class in 8 minutes later, so I had to leave. So I think the Dr. Wu will be the session chair. And I think our other two organizers, Dr. Qing and Dr. Chen, will also be here. Right? Hi, Jake.
Yeah, I'm here.
Okay,
yeah.
So thank you, everyone, and it's really glad to hear so many high-quality talks, and I hope you guys enjoy the rest of this this workshop. And I know that Dr. Wu is what's the time there in Austria?
Almost 12 in the evening.
Almost 12. Okay, so sorry, so you have to maybe have two more hours. Thank you for the effort. Okay, so
it's fine.
Yeah. Okay, thank you, and see you guys later.
Yeah,
Bye.
thank you.